Hello, Math 157ers. I'm going to do a short recording in section 7.3, talking about the concepts, but also talking about how to utilize StatCrunch to make the computations much easier. So this is a slide from 7.2, and just as a review, we're looking at the formula for the mean and standard error. The mean is equal to the proportion, and the standard error, sometimes called the standard deviation, is equal to the square root of the proportion times 1 minus the proportion over n. Okay, so the mean of the sampling distribution is equal to the population proportion. Second, look at where the n is. So the n is underneath the square root over here, and I hit the wrong button. Bear with me. So if you look here where this n is, that n is in the denominator underneath a radical. So if we were to increase the sample size by a factor, let's say we increase the sample size by a factor of 100. Okay, so if the sample size were to increase by 100, then the standard error will be decreased by the square root of that factor. So if we increase our sample size by 100, standard error is actually going to be decreased by 10. The square root of 100 is 10. So these are from 7.2, but we just want to kind of go through the steps. Only 65% of insured women get annual Pap tests. Find the mean and standard error for the sampling distribution with sample size 500. Okay, so the mean is the proportion, or 65%. Now, be careful, because sometimes in your homework it will want you to give a decimal or whole number. So 0.65. The standard error is calculated by 0.65 times 1 minus 0.65 over the sample size of 500, which is 2.1%. But on a decimal, we would write that as 0.021. All right, let's just talk about the trouble with P. So the main application of sampling distribution is to address the bias and precision of a sample that is taken. Okay. The purpose of taking a sample is to estimate the population proportion, because we don't know the population proportion. The standard error of P, it cannot be calculated because we don't have the size of the whole population. Okay, and this is why they're talking about sigma p hat, talking about the whole population. So we're going to do an estimate for P. So we're really going to do an estimate for the standard error. So p hat is typically your points. In the previous example, would be your 0.65. All right, so now we're going to talk about section 7.3, because that was a nice little review, and the central limit theorem for sample proportions. Now here are 4 examples. Okay. P, in the first example, n is 30, p is 0.5. It looks pretty symmetric around that 0.5 because probability of success or probability of failure is 0.5. Here, in the one below it, n equals 5, p equals 0.2. You know, it's a right-tailed distribution. We have a really small sample size. Can't say much about that. Here we have n equals 10, p equals 0.9. Small sample size distribution is going to be left-tailed because the probability of a success is 0.9, so more things are going to end up over this 0.9 column. Now, look at this. When we have a very big sample size, n equals 100, p equals 0.7, look, the 0.7 is your midpoint of your sample distribution. Just like here, n equals 30, p equals 0.5. That's your mean. With these small samples, we don't see this nice symmetry. But if we were to take n equals 5, p equals 0.2, we were to change this to n equals 500, we're going to see something that's going to have the mean of 0.2, and it's going to be symmetric around that mean. Okay. So whether or not, using the central limit theorem for a sample proportion, Okay, the sample first must be collected randomly, and the trials are completely independent of each other. Just think about flipping a fair coin. The fact that you got heads on the first flip is not going to influence whether or not you get heads or tails on the second. Now here's a big rule. The sample needs to have at least 10 successes and at least 10 failures. So remember, the probability of success is P. Okay? And the probability of a failure is 1 minus P. So back to that previous problem where we had the 65% of women having the BAP sphere, our N times P would be 0.65 times 500. We need to pull up our calculator. So 0.65 times 600, or 500. Is 325. So the number of successes we would expect to have is 325. Now, our N times 1 minus P greater than or equal to 10 is going to be 500 times 1 minus P, which is 0.35. That needs to be also greater than or equal to 10. Now, some of you might be able to guess what this number should be, but let's see if how close we are. 500 times 0.35 is 175. So our number of failures was 175 in the previous samples. Now, if you look, 325 plus 175 equals our 500. So if you know sample size and you know the number of successes, you also can subtract to find the number of failures. So we do have a big enough sample. Let's go back here and erase so we can move on. Okay, and the last one on this slide, large population. If the sample is collected without replacement, then the population size is at least 10 times sample size. So if you think about it, there has to be sample size is 500. 10 times 500 is 5,000. There are more than 5,000 women in the U.S., so that would be okay. Okay, so let's talk about the central limit theorem for sample proportions. Now, when we talk about the trials are random and independent and the sample and population sizes are large, then the sampling distribution of P hat is approximately normal and follows N parenthesis P comma P times 1 minus T over N. So it's really N. And your P is your mean and comma your standard error. And since we don't really know P, because we don't really know what the population proportion is, we're going to use P hat. Okay. All right. So 200 randomly selected American drivers were asked if they texted while driving. 48 of them admitted that they did. Excuse me, I'm being recorded. I have yours in my wallet. So this is the problem with having to record in the afternoon. All right, so 48 of them admitted that they did. So what is our proportion? Okay, well, first of all, we do have to make sure. Drivers are randomly selected. 48 successes, failures is just 200 minus 48, which is 152, which is greater than 10. Okay, so we are good to go. All right, so okay, the population of American drivers is very large. It has to be greater than 2,000. So we can conclude that this distribution is approximately normal. How do we find the mean? Well, it's just the number of successes over the total number in our sample, which is going to give us 24%. And the standard error is p times 1 minus p divided by 200, or approximately 0.03. Okay. So we were able to use the central limit theorem. And we're going to come back to this problem. Random sampling is often impossible to use. Other sampling techniques are often used. You can do systematic. You do cluster. There's a whole bunch of things you can do here. The voluntary response sample gets us into a lot of trouble. That's when you just send out a survey to a whole bunch of people and they send it back because only people who wanted to do it did it. Okay, so just be aware of these requirements. Typically, the population of interest is very large, but if you were trying to do this where you knew your population was only 3,000 and you decided to do 500, that's not going to work here because 10 times 500 is 5,000, which is greater than your entire population. Okay. Let's do a problem with the central limit theorem. 78% of all lab mice can make it through a maze. If 600 randomly selected mice attempt the maze, what's the probability that more than 80% of them will make it through? All right, so all requirements are going to be met here. The probability of one lab rat making through has nothing to do with the probability of another one. If we checked, we have random sampling. Our number of successes is n times p is 468 is greater than 10, and our number of failures, which is 600 times n minus 1 minus p, is 132, which is greater than 10. Okay, there are more than 6,000 mice in the world. I'm sure there are more than 6,000 mice that are even just in research labs around the United States. Okay, so what's the probability that more than 80% will make them through the maze? Okay. We know that the sampling distribution is approximately normal. Our mean is 0.78, and our standard error is calculated to be 0.017. So we write our sampling distribution as n. There's our mean and our standard error. Okay, so we're going to use StatCrunch. So if you look here, this is a screenshot from StatCrunch. We want to find the probability that more than 80% of them, if you look here, mean 0.78, standard deviation or standard error 0.017. Trying to find the probability that x is greater than or equal to 0.8, and there's our probability. So let's go through the steps. 0.3. I'm just going to go straight into one of these, and I'm just going to use both StatCrunch. So calculators. Sometimes I forget. Stat calculators normal. Our mean was, let's go back to our problem, 0.78, and our standard error is 0.017. I'm trying to find the probability that x is greater than or equal to 0.8. Compute. And there we go. There's our area in the red. Okay? And so since we were able to assume that we were able to say that the normal, we can use the normal probability distribution, that's how we get to it. All right. How about this? About 0.5% of all people in the world are living with HIV. We want to find the probability that out of 1,000 randomly selected people, at least 1% of them are living with HIV. So we'd really want to find, the probability in terms of StatCrunch 0.01. Can we do this? Well, n times p, and I know I already wrote over it, but n times p is 1,000 times 0.0005 because I said about 0.5%. So that would be 0.5%. So 5 is less than 10. We can't use this. So the central limit theorem does not apply here. So we cannot use the normal distribution to calculate this probability. All right, let's look at a problem or two from the homework. All right. According to the Regional Bar Association, 66% of the people who take the bar exam to practice law in the region pass. Find the approximate probability that at least 74% of 100 randomly selected people taking the bar exam will pass. Okay, so we don't have everything we need yet. So let's just use this. I'm going to just use this as a whiteboard. Okay, we're not worried about this CLT, but so, okay, 66%, that's going to be our mean. Okay, so our mean is 66%. Our N is 100. So we need to make sure the CLT applies, our mean, okay, which is also our P. So N times P is 66. That's good. N times 1 minus P okay, 34. So we're good. And let's see, there are more than 1,000 lawyers in the world, because 10 times 100 is 1,000, so we're good. All right, so first thing we need to find is our standard error. At 0.66 times 0.34 divided by 100. Take the square root, and I've got 0.0473. It's hard for you to see, but I'm coming up with 0.0473. And actually, if I rounded that, it should be 0.0474. All right. StatCrunch. Stat calculator's normal. Mean is 0.66, 0.0474, just making sure. And then we're trying to find the probability that more than at least 74, so more than 74%. X is greater than or equal to 0.74, compute. And we've got a tiny little percentage, which makes sense because our mean is right in here, 0.66. So 0.457. So actually, I'm really lazy. I do Control C and Control V, and I've got to round to 3 decimal places. 4456. And there we go. Let's look at number 3 on here. Okay. You sent out 3,500 invitations to hear a speaker, and you must rent chairs for the people who come. Usually about 11% of the people invited have to come. On average, what proportion of those invited do we expect to attend? The first time I did this problem, I kept trying to give them a number, but they want the proportion, which is about 11% come. So my proportion is going to be 0.11. All right. Suppose you assume that 11.5% of those invited will attend. So you rent 403 chairs, okay? Because 0.115 times 3,500 is 402.5. So you have to rent 403 chairs. You can't rent half a chair. What is the approximate probability that more than 11.5% of those invited will show up and you will not have enough chairs? Well, we're not going to worry about this outcome because we're going to be using StatCrunch to do our work. So come back here. Let's erase all this. Sorry, it takes a minute. Just a nice big work surface. There's probably a shortcut way, and you guys are at home going, oh, all you had to do was this. And I didn't. But if we look, 11.5, so, you know, the n times p thing here, make sure that we're okay. 0.115 times 500, you know, that's greater than 10, and then if we did 1 minus 0.115, 0.85 times the 3,500, that's obviously going to be greater than 10. So we're good. So what we need to do is we need our standard error. Our standard error equals 0.115 times 1 minus 0.115 divided by 3,500. Because we're using 11.5 instead of 11%. And I unfortunately got rid of my calculator. Hopefully it'll still show up on your screen. So right now I'm just taking out the calculator at point. I'm getting a tiny standard error. Okay. I got my standard error to be 0.00539. That's tiny. And we really just need to find the probability that X is greater than 11.5%. So they got left boundary. Okay, so let's find in StatCrunch. Now, what did they use? Let's make sure. Oh, and see, I've already done this wrong because our mean is actually 0.11, and I was using 0.115. So our standard deviation is going to be off. Let's go back here. Okay. If we can still see this app. So 0.11 times 1 minus 0.11. Divided by 3,500. Take the square root. 0.00528. 0.00528. So that's really all that I completely messed up on. Probability that x is greater than or equal to 11.5%, 0.115, 0.1718. So if we come back to that problem, we're a little bit off from here. Because they got 0.718, and they used that whole number for the standard deviation. Let's see, I think I marked this wrong. Okay, let's go back. So we have to be just very careful to use as much of this as you can. So we need to use 0.05288802. So let's go back to StatCrunch. We did not use enough. So 0.0052, how many 8s are on here? 3. And if you hit compute, now we got what that output gave you. So 0.1722. You go back to the problem. There it is. Those of you who are comfortable with your TIs, okay, normal CDF, that's the probability, 0.115 is the probability, is the left bound. 1, you would put 1 in as the right bound because it's all the way to the end. 0.11 is your mean, and then this is your standard deviation. I do not like to use the TI, so you can just go ahead and do that on here. The benefit of this is they want you to draw a well-labeled sketch of the normal curve. We know the mean is 0.11, so A is out, and D is out. Now if you look at your StatCrunch output, this is what your curve needs to look like. Look, here's your mean, 0.11. And it's the area to the right of 0.115 because we're doing greater than. So it's very, very easy to do that and just do that part from here. If we want to find the probability that more than 12% will show up, well, we can go right back to StatCrunch, and we just change the probably x is greater than or equal to 0.115 to 0.12, and it's right here. You're going to copy it and paste it back in. Just make sure you do your decimal places right. 4 decimal places, 1, 2, 9, 3, so we don't round up from there. How many chairs would you have to rent if exactly 12% of those invited intended? Well, to find out the number of chairs, all I need to do is do that 12% times the number invited, 0.12, because we need a number of chairs, times 3,500, 420 chairs. Why is my answer to part C smaller than your answer to part B? Well, that 12% is further away from the mean, right? So the probability that 11.5% of people, those invited, will show up is 0.722, or about 17.22%. Probability that more than 12% would show up is 0.029, which is almost 2.93, like 3%. Okay, so if you think about it, that 12% is further away from the mean of 11% than the 11.5%. All right, it's further out in the right tail than 11.5, and it's the tail that gives the probability of interest. So 12% is further along in that tail. If we go back and we look at our normal curves, look at this. The 12% is here, the 11.5% is right here. It's a bigger area. It's further out in that curve, and it's more standard deviations away from the mean. And be careful here. Answer part C is larger. No, it's smaller because 12% is further out in the right tail. There we go. All right, I think I've given you enough to be dangerous. I will do another short lecture on 7.4, and I wish you all the best of luck with this chapter.